Hey, so welcome back to our next episode of the Coffee Breakdown podcast. Today we have on Chris Orrico, who is a master's student at the Technical University of Eindhoven, and he's just finished his master's project. So, welcome to the show, Chris.
Thank you for having me.
Yeah, and I guess to start, let's just go a little bit about you. What's your background? How did you get involved in fusion? How did you hear about it?
So, I have a background in mechanical engineering, and I got involved in fusion because it was something that I came across during my high school education and thought, wow, this is this amazing engineering challenge that we could tackle as engineers. But getting involved, looking through it, I thought it was such a daunting physics issue, and the people who were working with it were such these just kind of genius physicists, and I forgot about it because I thought I couldn't get involved. And 4 years later, I had the opportunity to come complete the Masters of Nuclear Fusion here at Eindhoven, and never looked back.
All right, that sounds like quite a journey. So maybe first you could start and explain a little bit about your project in general words.
So to go into my project, I need to first explain what the lab that I'm working with does. They're called the Liquid Metal Shield Lab, and they're a new initiative here at the Dutch Institute for Fundamental Energy Research, who are looking into using this phenomenal technology called the liquid metal diverter, which is effectively a wall a wall of liquid metal held in place by a tungsten sponge to solve the issue of heat loads in fusion reactors. In the core of a fusion plasma, you're generating an enormous amount of heat, and all of that heat has to eventually be exhausted out of the plasma. Now, in order to get away from your wall melting when you exhaust that heat onto it inside of a fusion reactor, the people who designed this technology thought of, well, what if the wall was already melted? Along with a bunch of other benefits that this concept of liquid walls has for fusion reactors themselves. But the technology isn't quite there yet. So to be able to test it, they're developing this device called LIMES PSI, which is a beam of plasma that will test their target modules that will test that liquid metal technology. Now, where I come in for this is my project was to develop a method by which we continually circulate that liquid metal within that device such that the target doesn't dry out. And as crazy as it sounds, within these conditions, you're evaporating metal. What this looked like was me drawing on my engineering background to be able to develop a pipe system with a module that was small enough to fit inside the device and light enough to be held within the device, including a pumping system and a way for that target module to connect to those pipes. And then on top of that, incorporating things like sensors and electrical wires to actually melt the liquid metal and keep it at a constant temperature.
Wow, okay, so that brings us a little bit back to your background, how you said that fusion seemed like a very physics-oriented field. So, and you coming from an engineering background, did you find that there was a lot of value that you brought to the project, to the table, from having a different background than what you thought the field was about, let's say?
Yeah, and I think that if people were in my position where they're either a high school student interested in STEM, or if they're a bachelor engineering student who was like me and had no idea what they wanted to do with their career, fusion is this really cool technology that presents one of the biggest challenges for us as a species to overcome, and you don't need to be a plasma physicist to make a difference, to make a contribution in the field. And I really showed that with this project. I really leaned really heavily on that engineering background in a wide variety of disparate engineering disciplines, from fluid mechanics to system engineering to thermodynamics to just general mechanical design. And these were things that gave me an insight into the project that maybe somebody with a plasma physics background would have overlooked. I think one example of this is dealing with the issue of corrosion in fusion reactors. So we're working with liquid tin as one of the optional materials for this system. And when you operate with tin, it's good from the perspective of a fusion plasma. So from people doing the plasma physics modeling, it's a great material. From the perspective of an engineer trying to build your device, tin is terrible. Tin will corrode most materials that you use to construct, for instance, pipe ducts. So steels, tin will just pull the iron right out of the steel and effectively degrade your pipe. And the same case goes for things like copper, things like nickel. So you have to work around that and adapt to it when you're developing a fusion reactor, or in my case, this liquid metal loop. Another example was deciding how you're going to attach these target modules that are made of tungsten, to your actual liquid metal loop. The liquid metal loop itself is made out of steel. This is the best material to deal with the corrosion issue, but tungsten doesn't expand very rapidly as it's heated. So at some point that tungsten has to connect to your steel. And if the steel expands faster than the tungsten, you create a huge force at that contact point, and it fails effectively. So you can't weld those two pieces together. So that was another issue that was overlooked in previous designs that I was working off of for this project, that I feel that having the background of an engineer as opposed to somebody with a physics background really gave me a lot of intuition that helped make this project a success.
Right, and did you find that those skills that you had as an engineer transferred very well, or did you have to learn a lot more also in the project?
There was a lot of learning I had to do during the project, but I think one of the most important skills that you learn as an engineer that transferred to this is how to teach yourself. That's something that was really emphasized, at least for my mechanical engineering bachelor, is learning how to develop new skills and how to adapt to environments and use that skill to overcome the biggest problems.
And that's really the point of education, right?
Right.
Learning how to teach yourself new skills. And I guess if you had words for people who are interested in following your path, let's say, do you have any guidance for them? Where to look, what to look at, how to get involved?
Yeah, I think from my project, when you can lean on your background that isn't necessarily something to do with physics and can make a contribution to the fusion field, there isn't just a space for you here. If you have an engineering background, your skills are sorely needed within this field. You are needed to solve the outstanding system engineering problems and mechanical engineering problems that we have to deal with as a fusion community. Because it's all well and good if you can model the fusion plasmas, but if you can't build the device, then fusion goes nowhere. So for people who maybe are considering a future in engineering for their bachelor studies, or a bachelor engineering student who just is looking for a cool technology to sink their teeth into, fusion is this incredible field where we're developing effectively a sun inside of a bottle. And not only is there opportunity for you to work in this field, but I think as my project shows, you have a lot to contribute in solving those outstanding problems.
All right, great. And I suppose now I'd like to dig a little bit further into the technical aspects of your project.
Yes.
So, of course, you mentioned that you had this sort of liquid metal that you want to flow inside the tokamak. Now, as far as I understand, it's a electromagnetic environment. Metals are conductors. So how does that work?
So when you have a liquid metal flowing inside of in the presence of a magnetic field, if you drive a current in perpendicular to that magnetic field, and if the fluid is flowing in perpendicular to both the magnetic field and the applied current, you develop what's called the Lorentz force on that fluid. This is a electromagnetic force that effectively pushes the fluid in the direction perpendicular to those two fields. So what we can do is, instead of connecting an external pump that has things like rotating parts that may leak or that may freeze as the liquid metal solidifies, you can simply, because we have this external magnetic field already from our plasma device that this module is going to go into, you can drive a current just by simply connecting a copper wire or bus to that section of pump duct, and create a pumping head just by driving that current. And this is not only feasible within the pressure losses that we have to overcome, but it's also controllable. So you can define what flow rate you want at your what they call a capillary pore structure,
right,
which is this tungsten sponge that forms the structure of the target that the liquid metal is held in place by.
And what are some of the, let's say, advantages and disadvantages of such a let's say mechanism, right? Because I imagine also that the liquid metal itself has some resistance from trying to flow through an electromagnetic field,
Right.
right? And so are such devices, let's say pumps, capable of pushing the flow required by, let's say, in the end, the tokamak?
It's a very finicky solution.
Right. Okay.
The reason I say that is for several reasons. The first is that if you don't already have an external magnetic field, you have to create your own. And that's why these things are not very commonly used in industry for things like metallurgy. A lot of times when you're working with molten metals in metallurgy, you'll pump them using versions of this electromagnetic pump that generate their own magnetic field. Mm-hmm. Because we have our own magnetic field from this device, that makes things easy. We only have to apply the current. So that is one kind of environmentally situational benefit that we get that makes this possible. The other thing that makes this possible so that we can actually overcome the pressure losses of the system is the fact that the flow rates are very slow. The flow rate is in the ballpark because we go above this and below this, or are expecting to for operation. It's in the ballpark of around 10 milliliters per second. And you can imagine a flow going as slow as a drop from like a syringe.
Okay. And so then with that slow flow, you can avoid sort of drag in the pipes, or what is this
right. So
benefit of that?
We avoid just your traditional viscous drag, which is from the roughness of the pipe walls, from the pipe connections, just disrupting the flow of the fluid. Mm-hmm. The other benefit is you overcome the MHD drag. The MHD drag is what is introduced to the fluid as a force, not by our pump duct, but just by the very fact that there is a magnetic field. And this is caused by two phenomena. The first is you create what's called a Hartmann layer in the fluid, which is effectively you drive the highest velocity in your fluid very close to your pipe walls. This effectively increases the viscous drag at the pipe wall, creating more drag on the fluid. That's the minor effect. The major effect is the formation of eddy currents in the fluid.
Okay.
Normally, if you have let's say you have a conducting fluid flowing through a pipe that is completely insulating, those eddy currents close in on themselves inside of your conducting fluid, and in doing so, they create no net body force on the fluid. However, if you have a conducting wall, so for instance, for us, stainless steel, those eddy currents disappear into that conducting wall, meaning that you no longer balance the force on the fluid flowing through your pipe duct. What you get from that is you get a net body force on the fluid that opposes the fluid flow. And that's mainly what we're overcoming by our pumping system, is that this effect, even at our slow flow rates, because it is proportional to the velocity of the fluid, is an order of magnitude at least higher than your viscous drag. So this is the main thing that we have to overcome. And this is not only an engineering challenge for LIMES PSI, which is the plasma device for the LIMES lab, but also that we'll have to overcome if we have liquid metals flowing in tokamaks.
So do you have any sort of, let's say, lessons learned from the project that you've done on how to minimize such drag inside a tokamak, let's say, or how can we build such a system in a large scale machine?
From a theoretical perspective, the best thing you can do is insulate your wall from electrical currents.
Right.
The reason that we can't necessarily do this is you have to use ceramic coatings for electrical insulation. The ceramic coatings that we have that are compatible with liquid tin or liquid lithium, which are the two liquid metals that we're considering for this system, are difficult to manufacture. And they suffer from a similar issue that we had to solve between the tungsten and the stainless steel, which is that they have a much lower expansion rate when they heat up, known as the coefficient of thermal expansion, which means that as the pipe heats up, those layers are vulnerable to cracking. And if you crack the layer and then you wet the wall behind it, you've effectively reduced your insulation of your wall, and that becomes an issue.
Right. Also, yeah. So it brings back those eddy currents,
Right.
which we're trying to avoid in the first place.
The other thing you can do is you can cleverly arrange the geometry of your system. The effect of the magnetic field when the fluid is flowing perpendicular to the magnetic field is that MHD drag. However, when the fluid flows in parallel with the magnetic field, it has the opposite effect, effectively laminarizing the flow of the fluid, reducing drag.
Okay.
So if you can make as much of your pipe system parallel to the magnetic field as possible, because that pressure loss, the total pressure loss is proportional to the length of time that the fluid flows in perpendicular to the B field, you can effectively reduce the amount of MHD drag that you have on that conducting fluid. This is of limited consequence for the system that I was developing because I was constrained by how long the target needs to be for Lime's PSI. But in the case of tokamak, you absolutely need to make sure that that section of the diverter target is as short as possible because that section is perpendicular to your magnetic field.
Right. So in the end, it might be possible to use this electromagnetic pump in liquid metals inside the tokamak if we just design the geometry of your pipes.
Right.
Well, let's
Right.
say. Okay.
And this kind of circles back to what I was talking about earlier with the role that engineers can play in developing fusion. This is something that you would really only come across with when you're considering the design of a tokamak if you are really delving deep into the MHD effects of flowing liquid metals. So people need to be focusing on these individual things now that we've kind of got an idea of what the big picture will look like for things like the demo reactor. Is if you want to incorporate this in it, you need to really consider, is there space within our reactor to be able to flow liquid metals such that we can pump them, for instance?
Right, cool. And also then coming back to how did you find this electromagnetic pump concept? I imagine because it's so niche and has very particular places where it can actually be applied, it's probably not well known in literature. Like, how did you come across it? Did you find it on your own?
So, thinking back, the way we came across it was sort of a part of the design process. So for proper engineering design, especially for somebody who's doing a master's project and you have to write all of your steps down, you need to follow a design framework. And the design framework that I was following included a step that was the ideation phase. Basically working with the stakeholders of the Lime's or the Lime's lab to set a bunch of design criteria that this system must meet. And then you, instead of coming with a solution to the design and then trying to paint a bullseye around the arrow you've already fired, you obviously want to create the bullseye first, and that is this design criteria. So from there, we begin to consider, one, does the liquid metal actually need to be pumped? And two, what kind of pump can we use? And we had a bunch of different ideas, from making this a hourglass on a stepper motor that once the top reservoir of liquid metal empties, you just rotate it.
To let gravity do the
Right,
pumping.
exactly.
Okay.
There was another option to maybe have some kind of pumping system external to the vacuum vessel, because you have this vacuum vessel in which all of the magic happens for this plasma beam. But we have a pretty strict limit on the inventory of liquid metal that we can run, which means that really quickly, just by having pipes leave the vacuum vessel, you exceed your inventory limit, especially for lithium, where you need to reduce it such that a fire would not be catastrophic, because liquid lithium is extremely reactive with both water and oxygen. So from there, kind of whittling down the options, okay, we can't do the hourglass because it creates the danger of moving parts and shear stresses that you place on those joints inside the reactor, or inside the PSI device. We can't do an externally pumped system, so we have to have something inside the vacuum vessel. In trying to find a pump mechanism that was light enough to be able to be held in place inside the vacuum vessel, I was basically looking through options from suppliers online and came across the concept of first the electromagnetic pump. From there, I checked out a book from our school library on electromagnetic pump design and was going through, okay, can we build these ourselves? Because the designs are pretty complex.
Right.
Especially for the ones that I mentioned that are generating their own field. And at the very back of the book, in like a throwaway chapter, the book had this design for what was called a DC electromagnetic pump, which it basically kind of waved off as you would never use this because you don't have your own magnetic field. Because you have to have permanent magnets for it. And I was like, wait a minute, we have our own magnetic field. So they basically had a basic design solution for how you build one of these things and then calculate the pumping head that it generates. Though the solution that they offered was very rudimentary. It makes a lot of assumptions about the current density field inside of the pipe duct that just from the knowledge of how the eddy currents work, I knew was wrong.
Okay, I see.
Not necessarily wrong, but a very rough approximation. So I then took that geometry for the pump and made a simulation inside of a software called COMSOL, which basically is a software that allows you to do calculations of complex physics phenomena and couple them such that you can calculate things like the force due to what's called magnetohydrodynamic forces on your liquid metal. And it turned out that from the physical model inside of COMSOL and the very accurate simulation of that generated fluid force versus the analytical model that was proposed by the textbook was within 10% error, which for engineering purposes is fine. Because ultimately we need to measure the flow anyways, so you'll have just a feedback controller involved in your pumping system. Right,
okay. But that seems like quite a journey to arrive at this final solution.
Yeah,
absolutely.
And this was like 1/6 of the project.
Yes. Wow, that's good. But that's also very interesting because it has the benefit also of having no moving components. Meaning that it's very easy to maintain and very easy to have inside the reactor where we can't touch it.
Not only do you have no moving components, but you also never make a physical contact between a material that is incompatible with tin or lithium and the liquid metal, because you braze your electrodes to the outside of the pump duct, and the pump duct is just the pipe material.
Right. So it never touches anything except the pipe.
Right.
That's really nice then. And I think you mentioned earlier this COMSOL program, which actually kind of leads into the rest of the questions, because you said there's only 1/6 of your project. You had other components that I think you mentioned before, this interface between the titanium and the tungsten, or sorry, it was something
steel
else.
And tungsten.
Steel and tungsten. Yeah. And there was another one dealing with corrosion. So all of this, I suppose, was done or analyzed using this COMSOL software, or how did you take a look at this phenomenon?
So with the engineering design project, both due to time constraints and due to the lab safety issues that operating liquid metals presents, I knew that I was not going to be able to have time to build a prototype. So then you go to what you would maybe call the pre-alpha phase, which is proving the concept of all of the different design components inside of a simulation environment where you can't, for instance, light a lab on fire.
Right. Please don't.
So COMSOL offers you this really cool simulation environment where you aren't limited to a particular physics module, like, for instance, a structural mechanical study, where you can apply the finite element method to a broad range of physics, and then if you need to couple them, sometimes the modules exist for coupling. So, for instance, relating thermal expansion to structural stresses, that's one that exists between two separate physics modules in COMSOL. For the pump duct, I had to do it myself. So they have a fluid flow module for laminar flow. They have a module for electric and magnetic fields. These two things don't interact unless you force the program to make them interact, which means introducing a body force to your fluid equations that represents this Lorentz force that you generate from the magnetic field and electrical current. And then on the other side, introducing that fluid flow of a conducting fluid because it generates the eddy currents, and then that adds an additional loop of feedback that changes the solution.
Okay.
And you have to have a fairly thorough understanding of how all of these equations work and how they interact to even write one of these things.
Wow. So you wrote that yourself as well. Or
Luckily, I only had to write the coupling. The rest of it's already written in there.
Okay.
But
but it's still quite impressive, I would say. And then all of the like structural studies.
Yeah.
All of that was done in COMSOL as
Right.
well. Okay. And it can handle all of these things, and it's sort of compiled program.
Right.
But of course, you had to learn that from somewhere. So did you learn that software in this project, or did you
Yes.
have that from? Oh, you did. Okay.
So I have some background in design engineering, so building 3D models, and then doing meshing operations on them. So basically developing the finite element model for the finite element method, FEM, two separate acronyms, but you then have to apply your physics boundaries and your relevant equations to that model, and then how to do that in COMSOL was an entirely new thing that I had to learn going into this project.
Right. Okay. But I imagine that having your background in engineering already made you familiar with some of the concepts that the model is working with. Right. So things like the finite element analysis and just heat transport and all this sort of stuff.
Exactly. If I didn't have the courses on the fundamental physics from my engineering degree, plus the experience using the finite element method in similar programs to COMSOL, I would just have no idea where to start. But it's sort of like a linguist trying to learn a new language, or a programmer trying to learn a new programming language. Once you've done one, it makes it a lot easier to learn the next one.
Right, okay. And this is another advantage for people who have had that background to come in and do these things for the field, right?
Right.
Because I can see that a traditional physics major would not have any idea where to start with COMSOL. Of course, they could try, they have the technical background, but they would start from a different place than someone who's already familiar.
And they might use it to develop like a plasma physics model. Or like I don't know enough about physics. I just keep going back to plasma because that's what I learned from my my master's studies. But if you go the other direction of, okay, we have this engineering design problem, and then this software suite provides us a solution to answer open questions we have about functionality, then you're going in the opposite direction. And if you've taken classes on how to do finite element modeling, then that apply the finite element method. That makes that a tiny bit easier, a little bit easier, and you get more intuition. For example, if you didn't have the intuition that a mechanical joint between tungsten and stainless steel might fail, you would never take the next step to model it for that specific phenomena to see if it fails.
Right, exactly. You wouldn't even know to check that this is a potential issue. Right, okay. And so I guess how did it feel like to do, like it seems like it was a massive amount of work. How did it feel like to do it inside a master thesis? Was it mostly of your own, volition? You willingly chose to do all of this, or was kind of the project was put there, but all of these things were involved with it, and thus you dug into it?
So I had an idea of what the project would be. I had no idea that I would get so deep into the individual problems, because it would be, okay, these are the solutions that I propose. And then as I'm like working through the solution and trying to optimize it for the operation within the device, I kind of scratch my head and go, I didn't think about that. I should double check that works. One example of this is with the method that we use to melt the liquid metal for the beginning of operation. We need to keep the metal below a certain temperature threshold, which is about 50 degrees Celsius above its melting point, because as soon as you get 100 or 200 degrees above your melting point, for tin especially, the corrosion rate increases exponentially.
Okay.
So it's really important that we don't accidentally create these hot spots in our system. The other issue is that if you are melting your liquid metal unevenly, you suddenly create a pipe pressure in that location of your system, which could lead to, in some cases, maybe bleeding at the actual CPS surface, or the bursting of your pipes. So then that led to, okay, how do I set up a thermal model inside of COMSOL to be able to simulate the geometry of this electrical tape that we plan to use or electrical wire that we use to heat the liquid metal? How do I set the boundaries how do I make it that stand-in geometry and then set the proper boundaries? How do I introduce a control system to this? And that became like its own whole project within this project, and that just gives an example of how a simple question about functionality spirals into one of these huge studies inside of the software.
Well, that's sort of one of the, what do you call it, eternal things about research in general, is that you always ask a question and then you find there are more questions than answers.
This is our problem, is we ask too many questions.
I don't consider that a bad thing, but maybe for producing a final product, yes.
Yeah.
Eventually you have to say, okay, this is good enough, right?
I think my supervisor, Thomas Morgan, who's the head of the group that I was doing this research for, really helped me with that and stepping in and saying, are you sure that we need to figure this out? Is that really a necessary answer that we need to have?
Yeah, it's good to have a balancing force, or else it's very easy to just go into the weeds completely.
Right.
Yeah, okay. And I want to take now a completely different segue, because I remember from a previous conversation we had that you were into sort of like the economics of fusion, or at least the economics of energy in general. And I'd like to ask you a little bit on, from what you've seen in your studies or in your research about it, how are people talking about fusion in sort of this economic environment?
Unfortunately, outside of our sort of research niche, there isn't a ton of talk about how fusion can present a solution to the issue of the economics of renewables, for instance. So decarbonizing your grid. Mm-hmm. But fusion, just from my own studies, does, and from papers that have been written about what the economics of fusion will be once it's actually brought to market at the latter half of the century. The traditional renewables that we have today, so solar, wind, even tidal power, they're distributed, so they aren't centrally producing this electricity. You have to take it from wherever they produce it and transmit it to your market. That presents a source of loss, and the additional issue is that they don't have a continual production expectation. So you can estimate how much you're going to have in terms of sun or wind, but from the perspective of a grid operator, that is a level of uncertainty that they have not yet priced into their market.
Okay.
So what fusion presents is rather than having that unpredictable source of energy, fusion could be what they call the bid stack. So your base load operator is your cheapest, most reliable source of energy. It's an open question whether solar and wind can provide that reliably for a wide variety of markets. There are ones that it does, but that's the position filled by your things like nuclear fission, like coal production, natural gas production in some cases, or in areas where it's feasible, hydropower.
Okay.
Now, fusion can provide that position in the market, which once we completely decarbonize our energy portfolio, you really only have hydropower, geothermal, and nuclear fission producing those electricity sources. Hydropower and geothermal are very geographically restricted and are already widely exploited. Okay. So there's not a ton of room for growth.
Right, so the places that can accommodate it are already being used as an energy source, more or less.
From an economic perspective, nuclear fission can do it all on its own. That could absolutely fill you could make a decision tomorrow that we're going to produce all of our base load with nuclear fission, and it would be decarbonizing the entire world energy economy in a generation. But that's where you run up into the political reality where it's really hard to convince people to put a nuclear fission reactor in their backyard, no matter how reliable it is.
Right.
Which is, from the perspective of us as people who work in this field, we're like, that's stupid.
It is a bit silly, I will say it, but at the same time, I do see the concerns, right? We also know a bit of the science to say that, okay, I see where they're coming from. But at the same time, we've done so much to make it not that, right?
And you do so much damage with things like, if you have a coal plant in your backyard, that's going to do way more damage over your lifetime than even the worst operated nuclear fission reactor would.
That's true, yeah.
But we live in a democratic society. Like at the end of the day, you got to convince people, which is where nuclear fusion comes in, which is a source of energy that does not present the dangers that people think fission presents. That can provide this role of either baseload production or sort of middle of the bid stack production, where you can ramp down and ramp up your power in a period of about an hour. And it does not present a threat to that market that is next to it, whether that threat is perceived or actually real. So fusion will play this enormous role as that centralized producer where you don't have other sources of renewables. And this, based off of the estimates made for fusion markets by the end of the century, will constitute about 14% of the energy market.
Okay, that's an interesting statistic. So I have a question on, like, of course, that's making a lot of assumptions
Right.
about how fusion will progress as a technology and be incorporated into the market. So I imagine there's a fair amount of uncertainty there because you're projecting into the future.
Absolutely.
So how is that accounted for in this sort of 14%?
So from what I've read from the paper that wrote that number, I think it was the Eurofusion like pathway to fusion studies. There was a collection of them. I may have gotten the name wrong, and whoever wrote that and possibly listens at this is going to be screaming at me.
We apologize.
But I'll try to represent the work well.
Yeah.
Which is that they built in a lot of conservative estimates into this, which is conservatively estimating the price of the reactor, conservatively estimating how expensive electricity is by the end of the century. But then they basically point out that by the end of the century, you increase the global energy market so much just by the fact that the human population is growing, that something will have to fill this hole in the market. And if something doesn't fill it, like fusion, the price of energy goes up, which means that even if your reactor ends up being more expensive or having a longer timeline to come to fruition, or if you can't sell the electricity for as little as you thought you could, then even then there's a place in the market which reduces the effective uncertainty of that final percentage of the market number.
Ah, I see. Okay.
On the other hand, there's the possibility that the opposite happens, where one of these very dynamic fusion startups comes in and achieves deuterium-tritium fusion in the next 10 years.
Right. Of course.
I don't necessarily think that is likely or unlikely, but if it happens, then all of those calculations change and you commission new studies, and fusion comes to market way faster and has more time to corner a larger part of the market, especially during the next few decades when governments are scrambling for sources of renewables.
So one could say, in a very general sense, that 14% is a pessimistic
Yes.
what
Yes.
do you call it, estimate already.
Yeah.
Okay, that's heartening for me to hear. Let's put it that way. And I guess it's also interesting to know, like, how this sort of risk analysis is done, right? Like, do they just follow? I imagine it's a very complicated system.
Yeah.
Social dynamics and economics in general, and then you have to add on top of that all the fusion science that, of course, has its own timelines and issues. How does that risk analysis happen? Do people just pick a scenario and say, okay, we're going to assume this is the way it is, and then follow the ends?
Yeah.
Or do they really go like all out, like every possibility?
They typically follow a few scenarios, and it centers around, as I understand it, two central mechanisms. The first is I'm blanking on the name of it. It's been so long since I did this in my bachelor, but you have your what's called levelized cost of electricity, which is how much it costs to build the plant, how much it costs for fuel, how much it costs to operate and maintain the plant, and then what percentage of the year during that production period the plant is actually available. And they put the estimate somewhere between 75 and 85% of the year for availability.
Okay.
Then you compare that to I'm blanking on the second mechanism. You compare that to the effective demand for that market. So once you have that calculation, you can figure out where that fits into the thing that I referred to called the bid stack, which is basically what your grid operator looks at when they're trying to decide who they're going to buy electricity from. Now, based on that levelized cost of electricity, that takes into account all of those things from your maintenance level or maintenance requirements to the cost of just the thing you're using to fuel your electricity. You can decide where in that bid stack you'll be, and then based off of where you are in that that energy portfolio that is purchased by the grid operators, you can estimate what percentage of any given market you'll be a part of,
Okay.
and then how much you can sell your electricity for if we're still selling electricity.
Right.
Which is something that is possible, that we don't even have this market paradigm in 100 years. It would be interesting to see what replaces it, but that's always possible. Now, I don't think that they take into account the entire shifting of a market paradigm by that much.
Okay.
So they're still working within the economics of today. The other thing is the doubling speed for a new technology once it comes to market. So even if you solve fusion tomorrow, and every grid operator in the world wants to have a nuclear fusion plant built in their market, you still have fundamental limits to the amount of production that you can do, to the rate that you can actually build these plants, and that puts a fundamental limit on your market rollout, meaning that even if everybody wants it tomorrow, you probably can't reach a certain percentage of the market within a generation.
Right. You can't just go from like 0 reactors to like 1,000
Yeah.
overnight.
Right.
Okay. And so it's very interesting because then it seems that, of course, in such a complex system, there's no way you can change every variable and see what the outcome is, but you can pick, let's say, the more realistic versions of particular things and then just do a few variations.
Yeah.
Really the unknowns around it. Is that how it's done, or?
Yeah, and I think that also creates a trap. And we saw this with the rollout of solar and wind,
Okay.
which is a lot of like energy economists who do this as a career looked at this and went, no, we can't just replace everything in our grid with solar and wind. That'll create huge issues. And then maybe there were issues for the last decade, but we now have had examples of countries, I believe Denmark and Germany in the last like 100 days have run 100% of have had days where they ran 100% of their grid on renewables. And I believe California has had the same milestone, but that's not a full country market, even though California is huge. So there were people saying that this will never work, and we've already shown that it will. So we have to be cautious when taking the most conservative outcome, because sometimes, as we've shown from the traditional renewables, those biggest worries about how you bring these things to market and how they interact with existing grid structures aren't necessarily true.
Okay.
The other thing is when you're looking at investment in fusion. So people who maybe want to put money into the institutional research or into these private companies that are looking for funding, they price in not only the risk that this thing does not come into market, but also the opportunity cost of their competitor investing in it and making it work.
Ah, I see. Okay, so this is sort of the opportunity cost, let's say. If they do it, then they run the risk it doesn't pay off, but if they don't do it, they run the risk that it does pay off for someone else.
Right. If you're like a venture capitalist investing in renewable energies, there is probably a pretty decent, like if you are planning for the long term, there's a decent risk by you just not ignoring fusion. Because you don't get to have your finger in the proverbial pot once fusion comes to fruition.
Right, exactly. The people who have already done the investment kind of get the lion's share, right? They get first dibs on everything.
And even in the case where your particular company that you back, company or research institution that you back doesn't have overall success, you still probably will get some patented technology out of it.
Right.
This was kind of the big selling point one of the big selling points from Commonwealth Fusion System is they had this very innovative manufacturing technique for superconductors. And I think just from looking at it, again, this is me speculating somewhat, but the people who were investing in that company were saying, even if their fusion dream doesn't necessarily come to fruition, there's a ton of other applications for their superconductor technology, so we would be stupid not to invest in it.
Yeah, and I was reading into that, and I was thinking myself, that's such a smart idea even from the researcher side.
Right.
You say, here's our grand plan, but here's a much smaller thing that is a piece, like a crucial piece of our grand plan,
Yeah.
that we can do in the short term, which can already give return on investment, right? It's such a smart way to go about funding research and development in our field.
I would love to see more publicity about this, just from not necessarily the fusion companies because they already have their own publicity, but from like us in the research field. I wish we would get more messages out there about what we're doing because it's exciting, and you generate hype, and hype generates money, and we need money. So
and I think that's a good point to leave this one. Everybody needs money, but I think we're doing it for a good cause, right? So, fair enough. Do you have any final words for our listeners?
Yeah, I guess kind of circling back to my initial comments, if you are somebody who's a bachelor engineering student or even master's engineering student, or even a high schooler who might be interested in like engineering design, fusion is this amazing field that is desperately in need of your talents to help push us forward to the next big thing. So if you were like me and you weren't quite sure about yourself and maybe don't think that you have what it takes to make a contribution to fusion, there's absolutely place for you, and there's always angles that haven't been explored for the fusion devices and the connected engineering systems that need the best and brightest. So it's an awesome technology. Go for it.
Get involved, basically. Thanks again, Chris, for coming on.
Thank you.
It's a wonderful conversation. And for everyone else, tune in next time for our next episode. See you. Bye.